All right, welcome to lesson 4.7. Before we get started on this bell ringer, let me just kind of show you kind of where we are, what we're going to be doing. My computer, I know my internet is really scrunched right now, but that's because I'm going to use it that way for this lesson. What I'm going to do is go to your digital classroom. We're going to open up 4.7, and there's a few things I'm going to point out. So when we open up this document, here you listening to me means you're learning a lesson. So that's taking care of number one. Make sure you fill out your attendance. Number two, you can either scan this QR code or click that link there. I would recommend you open up the Power School Learning lesson exams and DOLs as we go. And don't forget about your homework later on. But specifically why I went here is I want to open up both these two, the list of pre-programmed calculators. And I would recommend you open up this unit circle help. That's going to open up this picture right here. All right, from the Desmos graphs, we're going to use quite a few of them today. Today we're going to learn about three new ones: the law of sines, law of cosines, and Heron's formula, which really finds the area of a triangle. We're going to learn on all three of those. But for this bell ringer, just click up number 14 for now. And the first thing I'm going to do is we're not actually going to deal with asymptotes today, so I'm just going to close that part off. And the reason I opened this, and I want you to be able to see the ratios, and we won't even need that there either. So I'll take that off just to clean it. And like I said, today the calculator is just going to stay on the side. That's why I have it small over there. All right, let's start looking at reviewing these problems. So as we learned in the last class, when we were doing inverses on lesson 4.6, we learned that we can use the unit circle to solve for inverses as well as normal trig functions. So before I use this, let me remind you from the left side of the screen here that sine theta equals y over h. Sine theta equals y over h. And this is true anytime the angle is what's been called the standard position, meaning it's on the x-axis. What we learned about last class is that the inverse, sine inverse, what happens is you swap the angle with your side lengths, like this. So there's the inverse. The inverse swaps those two, as you can see. They've been swapped. Okay, now with that, we also learned last lesson with inverses that part of the domain is restricted. Because it's restricted, we won't have to look at this full unit circle. So when you're dealing with an inverse, you can always restrict the domain. Sine's inverse restricts your values or the range that's produced to be what we see on the right side of the unit circle. These are the only values that are going to be true values because of our restricted domain. So we're only going to be looking at values over here on the unit circle, not going to pay attention to the left side. So specifically, I'm looking for the y over h, again, y over h, on the right side of this triangle. So I will start here. That's a value of 1. That's not it. I can move around. That one's it. And it doesn't matter where I start. I could have gone here. That's negative square root of 3 over 2. That's not it. Not it, not it, not it, not it, not it. There it is right there. So once you find your angle, what this is going to give you as your solution is, I said that backwards. Once you find your ratio, there it is, ratio, it'll find you the answer as in terms of an angle. This angle or this solution will be pi over 3. So sine inverse of square root 3 divided by 2 will equal pi divided by 3. On Desmos, it's just fantastic. You can check your answers. You can type in sine, and I'm just going to do to the power of -1. That works the same as going to functions and actually clicking sine inverse. You can do it either way. Let's minimize that back. Sine inverse SQRT for square root 3 divided by 2 gives me 1.047. Let's see if that's the pi divided by 3. I'm going to hit enter here to get a new equation. Pi, pi. Just typed in pi for that one. Divided by 3. Check that out. We got a winner. That would be the solution to number 1 there. Let's check out number 2. So now number 2, it says find the exact value of arctangent -1. By way of reminder, arctangent is nothing different than inverse tangent or tangent inverse, -1. So let me paste, that's not what I wanted. Thought I copied that earlier, my fault. Let me copy that. And now we'll paste it over here. Okay, so now we're gonna look for arctangent of -1. Well, tangent inverse has the same exact domain as sine inverse. Well, I shouldn't say same exact, because technically you would have a parenthesis, you wouldn't even have defined the y-axis either. It would be a parentheses, but it's very similar. You cross out the left side. That part's the same. You cross out the left, just on these spots would also pi/2 and negative pi/2 would be undefined. So I've crossed that out. So sine and tangent inverses are together in that regard, that you don't look at the left side of the unit circle. And so now I'm looking for -1 tangent value. Well, these values are given in the form of x comma y's, which is similar or the same as cosine comma sine on the unit circle. So what do? It says I'm looking for tangent. Well, I'm looking for then a y value that represents -1 and an x value that represents 1. So there's a couple of places that are curiosity. Here we have a y of, well, no, let me change that. We need a y to be -1. So let me go down here. We have a y of -1 right there, but the problem is x is 0. Well, that's not right, so that's not our point. And on this location at 0, 2 pi, we have an x of 1 that we needed, that was good, but we have a y of 0. Well, that's not right, so that's not it either. So what does this mean? Well, we get this with tangent inverses by reducing the value. So tangent inverse, it's kind of tricky in that regard because you always have to think about the ratios of y divided by x reducing one another. So really we're looking for two values that would reduce down to become -1. And so I'll do this, just do a little hook arrow like this. So I want you to pay attention to both x and y to see if they were as set as a fraction of one another, they would reduce to be -1. Those do not. Do these reduce to be -1? No, they're not the same thing. Do these reduce to be -1? If I took this and divided it by this, would I get -1? I would get 1 because they're the same numbers, but it would be positive because they're both the same value. So it's actually not that one either. So I keep going on, and sooner or later, we're going to get down to this spot right there. At this spot, I have a positive square root of 2 over 2 and a negative square root of 2 over 2. Basically, the hypotenuse is kind of like 2. I have an x square root of 2, y negative square root of 2. Those would reduce. Those would be the same thing as inverse tangent negative square root 2 over positive square root 2. So there we go. We found our spot. Now that we got that spot, we need to get our theta. So the answer is going to be whatever theta that's pointing at. Well, let's check that back. It says it's 7 pi over 4, but 7 pi over 4 is going around this way, and we've already eliminated that. So it's not going to be 7 pi over 4. Let me go ahead and connect that. It's not going to be 7 pi over 4 because that got scribbled out. What it will be, though, is the solution going this way. If I went negative, all the way around would be 8 pi's over 4. So this must just be negative 1 pi over 4. The 1 pi over 4 is what it's missing to get to 2 pi. It's missing 1 pi over 4. Since I'm switching directions, that's negative pi over 4. So all in all, arctangent of -1 equals negative pi over 4. Let's check our answer in Desmos. So I come over here, I'm going to switch this to tangent, and the value was -1. It gives me this crazy decimal. So we're going to check, is that the same thing as negative pi divided by 4? What do you think? Do my decimals seem to match up? You bet. That's the correct solution. All right, so we've seen sine inverse and tangent inverse eliminate the left side of the graph because their domains are very similar. Not exactly the same, but very similar. Cosine inverse's domain is different. So let's work out this problem. And not only that, this problem is a two function. It's a composition of trigonometry. So whenever you're working with compositions, we need to make sure we follow our math rules. So there's a math rule we learned earlier this year called Pemdas. What does Pemdas mean? That's right. Very good, Airly. That's just order of operations. What we're doing is we're saying to solve this, you need to first begin with the parenthesis. And so that's what I'm going to do here, is we're going to solve this little portion first. So we'll say cosine inverse of 1/2. Let's go solve for that. Well, cosine inverse's domain is a little bit different than sines and tangents. Where sine and tangent, I scribbled off the left side of the unit circle. For cosine inverse, you scribble out the lower side. The domain is only defined from and 2 pi as well. It's only defined from 0 to 1 pi. Let me take that back. Not the domain. The domain is from 1 to -1 or -1 to 1. The range, the solutions will be from anywhere between 0 and 1 pi. So I'm going to scribble that out. That's the only values we're looking at right there. So now let's go find 1/2. I'm looking for an x value 1/2. So I'll start here. Let's see, that's 1, that's not it. There's square root of 3/2, that's not it. Square root of 2/2, that's not it. There it is, 1/2. Notice over here we have a -1/2, but we're looking for positive 1/2. So my angle here that's generated, or the output, the solution, is pi/3. Okay, so why do we do that? Well, now that I've completed the inside of the parentheses, I can go on solving the rest of the problem, which says find the cosine. And instead of putting cosine inverse in this parentheses of 1/2, I'm going to substitute. We found out that solution was pi/3. So I'm going to substitute in a pi/3 right here. So we're going to find what is cosine of pi/3 to get our solution. So I've eliminated this part of the domain. It stays eliminated. So I'm only going to be looking up here, and we find out pi/3 is already circled. So now we just need to get the cosine, which is x/h. So I need the x/h, which happens to be 1/2. So this problem, we end up exactly where we started. We could have just said cancel, cancel, though that doesn't always work because of domain range changes. That will not always work. But typically, if you share the same function, your answers will be very similar in that regard. Let's type it in the calculator to see if it's capable of telling us the answer here. Cosine, parentheses, cosine inverse of 1/2. And you say 0.5, you hit the little fraction button on the left. It's 1/2, so we did do that one correctly as well. All right, let's finish up the bell ringer, taking a look at number 4 here. It says find the exact value of cosine inverse sine pi/3 if it exists. Okay, so piece by piece, doing PEMDAS again. You got to go in order. So I'll start with the front end, and we'll say, what is sine of pi/3? So when we take out the unit circle, looking for sine pi/3, which means, is this an inverse? No. I want to remind you, for sine and cosine, when they're not inverses, you use the whole unit circle because the domain's not limited. It's all reals. So you don't eliminate anything. So I first find pi/3. Now I want the sine, which is the y/h. So I take this value. I really circled the wrong one. There we go. That's my domain. This is my output. So this is the value that it produces. It produces an output or a range value, square root of 3 divided by 2. That's the solution for the inside portion. That's the exact value of the inside portion. But we're not done yet. We now need to complete the outside of the parentheses. So I now look for what is the cosine inverse And instead of saying sine pi over 3, we'll substitute square root of 3 over 2 in its place. So now that I'm doing an inverse, now I need to restrict my domain here. With cosine's inverse, what part do I restrict out? Which part do I cross out? The left side of the graph or the lower half of the graph? For cosine inverse. I'll let you look once. Number 1 was sine, we crossed out left. 2 was tangent, we crossed out the left. 3 involved the cosine inverse, we crossed out the bottom half. What part of our domain are we now going to cross out? The bottom. The bottom half goes away. And by the way, this would be true for secant. Let me widen this just a tad. This would cosine and secant would share the same domain. Inverses, this is like you would do the same thing. Sine, cosecant, so on and so forth. Okay, they share along those lines. Okay, so I eliminated that, and what am I doing? Oh yeah, getting an answer. So we're now looking for an x value because cosine's x over h. So cosine inverse, they're producing an x over h at square root of 3 over 2. So we look on the x-axis for square root of 3 over 2. I should have switched colors. Pardon me. Let me switch this to like blue. That's still red. Blue. There we go. Okay, so now let's shift this around until we find the x value that's square root of 3 over 2. Oh, there it is. And so this would produce the angle pi over 6 as an answer. Okay, I want you to notice this time. Sine and cosine, they're different functions. Even though the cosine inverse, sine, they're completely different functions, so the answer did not stay the same. It changed from a pi over 3 to a pi over 6. Even my denominator changed. Let's check it out over here. We're going to have cosine inverse. Just need to make that power -1 of sine, standard function sine, and pi over 3 here. Pi, pi, divided by 3. They give us this crazy decimal. We want to know, is that pi divided by 6? What do you think? Yes, it is. We got it. So that would be your bell ringer. Okay, now we don't need this calculator anymore. I'm not going to use it today, so you can close out. But what I would recommend for you is to open up calculator number 15, the law of sines. That's where we're going to begin right away today, the law of sines. So go ahead and open up that calculator, and we'll use that throughout the rest of the day. I'm going to close off some of this other stuff. All right, so beginning here with law of sines and law of cosines. What these do is they solve what we call oblique triangles. Just said another way, think of it as triangles that are not right triangles. So everything we've seen so far has dealt with either circles, graphs, or a right triangle. Inverse graphs and just normal graphs, but we have not dealt with triangles that are not right. And in the real world, we have plenty of these. So we have to have some more trig to solve it. And you're going to come upon two very powerful formulas or laws that solve any triangle that's not a right triangle. And actually, let me correct myself, these will solve even right triangles. So these will always work no matter what the triangle looks like. So you could have the craziest looking triangle like this. That still looks a little bit like a right triangle. Let me alter it. And you could use the law of sines and the law of cosines to solve these triangles. So do they always both work? No. The law of sines works in one situation. When you have what I call a pair, when you have a completed set is what I also call it. I'll put quotes around this, completed set or pair. Okay, I want to put quotes around the word pair and completed set. That's when you use the law of sines. So for example, the law of sines will work. Let me clone this and do law of cosines here. So like if you had, let's call this angle A, and this would be little a. If you had values here, I'm just making up numbers, you would use law of sines. because this is what I call a completed set. You have numbers representing the angle and the side length across from it. That's when you would use law of sines. When you use law of cosines is when you do not have a completed set. So when do I use law of cosines? When you do not. When you do not. Actually, let me erase that and make it caps. Do not have a completed set. Okay, and put the quotes around these again. All right, and this will complete this little part of notes here. That's the key for you. Now, a lot of students, after learning this lesson, will not use sine y, cos x, tangent is y over x again. They go with a different formula entirely. They'll just use these the rest of the way. This is going to be law of cosines over here. So let's just say I give you A is 20 degrees, and I give you B is, let's see, that's 10. This is a little bit longer. I'll call this one 15. And they give you C equals 25. Something like this, you would use law of cosines because you do not have a completed set now. All right, so that's the difference in the two of when you use one, when you don't use the other. I'll add a C here of 25 and a C, that would be a B and a C. Get proper labeling on your triangles. So that's when you use one and when you use the other. All right, so with that, I'm going to get started. These calculators are new to the school year here, 2021. I just created these, and I realized the last 8 years of me teaching pre-cal, I've been teaching this the hard way. I've been teaching people how to do algebra, and all I needed to do is just program a little bit into Desmos, and I'll tell you, it makes our life way easier. So I'll show you how this works. So here's the law of sines to begin with. Here's its formula. If you've opened up the calculator, you'll notice I typed in just the first part because for my calculator, I didn't want to program this. I didn't know how to program it to solve for 3 things at once. Desmos would give me an error. Watch. As soon as I hit a second equal sign, it alerts me there's something wrong with this. So I only took one side, but this is the formula. It says this: the ratio of the sine of angle A over its length will equal the ratio of sine of angle B over its length, or the ratio of angle C over its length. They will always equal one another. It's a very powerful formula. So again, this works when you have a completed set, a pair, like when you have this value and this value given to you. Okay, that would be like a pair, and you can use this formula. So let me just show you some. Now that you see the formula, let's work some of these out. So notice right away, I have a pair. I have angle 29 and side length 22. That's what I'm going to, let me write down the formula one more time. Sine A over A, this is what I'm going to use. But like my calculator, I'm not going to type in all 3 portions. I'm just going to type in the first fraction, not all 3 ratios at once. So frankly, what I'm solving, and my calculator will do in a matter of seconds, is sine of 29 degrees divided by its side length 22. There's the ratio for my, in this problem, technically L's. This is my L's ratio, sine of angle L divided by length L. And I'm going to set that equal to M. Sine of 112 over little lowercase m. So in previous school years, I got to this point and said, hey, you learn this. Most DISD teachers called this butterfly method, butterfly technique, where you cross multiply and divide. You would multiply your m times sine 29, m times sine 29, and you would set that equal to 22 times the sine of 112. And then specifically, I'm solving for m. M is multiplying. How do you get rid of multiplication? Division. To get m by itself, you'd end up dividing by sine of 29 degrees. Thus, the saying I learned, though again, most DISD students learn it's called butterfly technique. What I learned it as is cross multiply and divide, and we get our value. So I'll go to the calculator, and after doing all that algebra, I'll type it in and see what we get. sine of, or excuse me, 22 sine of 112 degrees. Make sure you're in degree mode here. Degree mode, good. Divided by sine 29. I get 42. I'm going to round to the nearest tenth today for everything. I'm going to ignore the instructions, just go to nearest tenth. 42.1 degrees. Not degrees, I'm sorry, it's a side length. 42.1. Okay, so that was a bit of algebra. We're going to have to do this algebra again. Or, here's the key, or we're going to use my calculator. Watch how fast this works. So instead of doing that algebra right there, what if we just would have come over here and said, okay, I have a completed set. That's going to be my A's. I'm going to put this as 29 degrees because the capital A deals with the angle 29 over 22. So I have 29 over 22. Literally, 29 is over the 22. I have 112, and we don't know what this is. I'm going to put it as the letter X. The answer, according, that's what it said to do, but the unknown is X. According to this instruction, the X value at the intersection of the graphs represents the solution. It says 3. The blue one just appears when I hit that. The answer is the X value right there. 42, and again, I told you I'm going to round to the nearest tenth, 42.1. Is that what we got? Now, which one was faster? Calculator. So now let me show you the other one, and this time I'm not going to cross multiply and divide. I'm just going to say, okay, if we're going to find this side here, I first need to find this angle. And so in a triangle, how many degrees are in every single triangle? 180. And so I take the 180 and I'll subtract the 29. And I'll also subtract this 112. Let me get what that number is. 180 minus 29 minus 112. That's 39 degrees. So now if I wanted to do it by algebra, I would do the same relationship that I had up here, except this time I'm going to take my sine of 29. I'm going to take this completed set again, sine of 29 over 22, and I will set it equal to sine 39 over n. And you could cross multiply and divide again, but I'm just going to use my calculator to find out what n is. I already have the 29 over 22 there. That is sine 29 over 22. Now my angle has become 39, so it's sine 39 divided by x. Click here. I find out my answer is 28.6. I round 28.6. That would be my n. All right. At the end of the day, using the new calculator, it just takes practice. So I got a DOL for you. You can use some algebra, but I would recommend you use this little over here as well, because you'll be able to check your solutions or solve it faster doing so. So here's your DOL number 1. All right, let's take a look at this second example. Now, the second example is a real world example here. It says a person is in a hot air balloon and observes a building, angle of depression to a building on the ground that's 65.8 degrees. After ascending 500 feet, the person now observes that the edge of the balloon, or excuse me, the angle of depression is 70.2 degrees. How far is the balloonist from the building? So to help us out here, let me give you some pictures. We'll make this be a building here. So this is my building that it's talking about. That's the building. And it says you have a balloonist that's like in a balloon. So if you just think about it like a hot air balloon, and I'll make a little blue person in there. They're like, hi, that's me. They look out, and from the way they look out, they notice that the angle to the building, and I don't know where necessarily, I don't think it says if it's the base of the building, top of the building, or whatever, is 65.8 degrees. So to make it 65.8, I'm going to go to the base of the building. I think that's more accurate. So that's like right there going to be our 65.8, 65.8 degrees. Now it says the balloon ascends. Ascend means it goes up in the air. So it all moves up 500 feet, just like that. And so they just ascended 500 feet to this point there. So I'll add in there 500 feet. And now it says that person looks out the window and notice the angle of depression. Again, angle of depression means you're looking straight out and then you curve your eyes downward. Is now increased and it's a larger angle to the base of that building. We're now going to say that that right there is 70.2 degrees. So we have to solve this triangle. So a couple little diagrams I want to draw to help you out, because a lot of students, I've been teaching this again 8 years, using this example quite a few times. I know a lot of students are lost on, wait, what do I do from here? And we have to find the distance from the balloonist to the building, but how do I get anything out of this triangle? I don't have much going on in there. Well, so here's what I'm going to do. I'm going to copy a couple pieces. Will it copy all three? Let's see. Yes. And rewrite them over here, because I want to remind you, if this is 70.2 degrees right there, this in itself is making a 90-degree angle. Okay, that's a 90-degree angle, and 70.2 of them are right here. So how could I find that angle that's on this side? How many degrees is a right angle? 90. And if 70.2 of them are right there, all I should have to do is subtract. 90 minus 70.2 should give me, I think that's going to be 19.8. That's going to be the angle right there, 19.8. Okay, not only that, I also want you to take a look at this, right? Well, let me click them all. There we go. I want to also take a look at this piece. We know that this makes a right angle here. So if I want to find the angle from here to here, this angle would be 90 plus 65.8. Are you okay with what I've done so far?
Yes.
Which means if I wanted to redraw this now, what I can do, or I'll just place it this way, I'll say this angle from here to here is going to be 155.8. Let me do this. I don't know how to symbolize that it's referring to the inside, but there we go, 155.8. So now we can actually solve the whole problem. What I can do to find this last little angle down there is I'll just subtract from 180. This angle right there is going to equal whatever 180 minus the 155.8 minus the 19.8. If you have your calculators, you can start to plug those in. I'll come over to the right and I'm going to type these in. Excuse me, I said right and I went left. That's ridiculous. All right, go over to the left side of your screen. I'll type this in. I'm getting 4.4 degrees left over. So I'm getting 4.4 degrees. So now I can actually solve this, believe it or not. I can solve this whole problem. You might be thinking, how can you solve this problem? I don't even know what we have, what we're even looking for. Well, what I do know is this. We are looking for this length from the balloonist to the building. That's the value we're looking for. We're looking for this length there. That's our unknown. And we have a completed set now. I know that I have a completed set of sine, the angle 4.4 degrees, over the ascension value of 500 feet. And so that would equal sine of 155.8 divided by the unknown. And so let's go type in our values. My completed set goes first. I have 4.4 here. I have 500 here. And then underneath it, I have an angle of 155.8. And an x is unknown. So I do have an idea it's going to be way bigger than 500. So the reason I'm not seeing is I probably just need to zoom out. Shrunk screen doesn't help here. When I zoom out, I do get my answer. We're rounding the nearest tenth today, so I'm going to say 2,671.6 feet. So 2,000, and this is approximately 2,671.6 feet is the solution here. All right, so I know this problem had a lot going on, and a lot of it was just figuring out the diagrams. But that's how you would do so. I have one for you to try. The diagram is going to be given to you, and it's really going to be basic math once you look at it. So here's one for you. Difficulty's quite a bit less. I'm going to add a line so you can see it easier. The problem says the tree is leaning 10 degrees past the vertical. That means instead of being 90 degrees up here, it's 100. It's been slightly changed to 100. You're 10 feet away with an angle of 42 degrees on this wire here. It wants to know how tall is the tree. So what you need to solve for is this length there. You're going to solve how tall is that length there. This is your second DOL. Make sure you come up with a completed set to solve. Let's go on to example 3. Now, example 3 leads us into this. With the law of sines, there is one situation where your answers can be extremely tricky. What do I mean by that? Well, if they give you one angle, where is it even shown? Okay, here, that's what I was looking for. If they give you one angle and two sides, they wrote the letter SSA, and they did that just to try to be more polite. But I think of it this way. If they give you one angle and two side lengths, you can have a variety of different solutions. You might have no solution, you might have one solution, or you might have two solutions. I think of it like this. If you have one angle and two sides, it's just going to be an assy situation because you're working with an ass. So that's inappropriate language, but sorry, it's funny. So anyways, that's what we're working with here. So check out the different options. I know this doesn't make sense, but this is assuming that if A is given to you, and let's say you know angle A, and maybe you know length B and length A. Well, there's some situations you'll find out where this length isn't even long enough to get down here because you know how wide it's got to be, and it just simply put can't make it. That would be a no solution. You might have one where there's just one solution. It's a perfect fit. But there is also the possibility of having two solutions where we know this angle, how wide it is, we know the length of B, and we know A is long enough it could hit to the left or to the right. There's two possible solutions. So I'll show you how that all works out using the calculator. The calculator really helps us on this one. So it says find all the solutions given the triangle if not possible. If no solution exists, write no solution. Round sine lengths to the nearest tenth, and we're just going to round everything to the nearest tenth. And they give us one angle and two sides. This is one of those situations I was talking about. If you have one angle and two sides, we could have no solution, one solution, or two solutions. So let's check out our calculator. Before I show you the drawing, I'm going to show you how Desmos, the programming of this, will really take off some of the guessing game from you, okay? So let's go and type in angle A as 63 degrees and side length A as 18. Side length B is 25. I don't know angle B, so I'll put an X there. Side length B is a 25. By the way, I didn't even draw this attention to this. We do have a completed set here. My A, I have a capital A and a lower A. So I do have a completed set. So this is the law of sines. When I look over here, I can zoom out all I want. I don't see any solutions. I don't see any red vertical lines intersecting. This is going to be a no solution. So wait, why is it a no solution? What visually is happening? Since I'm not the greatest artist, I'll have the visual for you right here. Here's the idea. This angle is 63 degrees. They told us it has to be this wide. They also told us B has to be a length of 25. So if that's true, we know the width here, and we know this has a length of 25. 18, no matter which way you swing it, maybe they put 18 this way, but we don't actually know how wide C is. But we know 18 represents a length that long. No matter which way you swing it, can it reach the bottom portion of the angle A to make a triangle? No. So for that reason, it's not a triangle. That's why there's no solution. They put that there, but I'll just show you that you could put this wherever you want, and it would never reach. And so that's the idea of what's happening. Without the calculator, it's a lot harder math. So it's very nice to be able to see that. I say that. What you're really going to run into is you'll set up your solution, or you'll set this up. By the way, this is giving you an idea that something's wrong up there when you get that warning. Sine 63 over 18 equals sine of capital B over 25. And you can do your cross multiply and divide, but you won't get a real answer. I think it might, in the old TI Inspire, say non-real calculation when you try to solve it. It just won't work out. Part B, let's try it again. So same instructions, here's our side length. So this time I come over here, I type in 105, A is 73. We don't know the measure of length of B, or the angle B, sorry, but we do know the length of B is 55. Now I'm so far zoomed out, again, the law of sines can be problematic because it doesn't always give you the right stuff. So I'm gonna press that home button to shoot me back home here. And now I'm gonna zoom out. And the truth is you can always have one solution, or excuse me, 0 solutions, none, 1 or 2. So I'm just gonna scroll out until I see the first 2. My calculator right now, as it is, will show you more than one. I'm gonna focus on these 2 right here and there. These are the 2 I'm gonna look at. I have a solution here. I have at least this solution. This one might possibly be a solution. So now I have to interpret what we're looking at. We are solving for angle B right now. And so the calculator has spit out that angle B is going to be 46.7 degrees. And the next angle is 133.3. Now I want you to think about it. If we had a triangle, so A is 105, that's more than 90. How many degrees are in each triangle? 180. Could you have another one that's 133 in there? Is that possible? No, that's not possible. So this one has only one solution and one solution only. So it's going to be angle B of 46.7 degrees. Since I now know that, I'll show you the actual picture. And so we just discovered this is 46.7 degrees. And now we can solve the rest of the triangle. I have that completed set, that completed set. With C, let's get that angle C here. I'm going to take my 180 and I'm going to subtract my 2 angles of 105 and 46.7. 46.7. I get 28.3. So this becomes 28.3 degrees. And so the last thing I'm looking for now is the side length across from 28.3. Now here's where a lot of students get boggled down. They think, wait, how do I get this last side? Watch closely. I'm going to use my calculator, but I'm going to treat the C as if it's the B. I'm going to plug that in. And so now I leave my completed set of AN, the 105 degrees, 73, that stays. But I'm going to change the B portion to represent the C portion. I know the angle is 28.3, but I don't know the side length. So I'll call it X. And that gives me the answer of 35.8. 35.8 there. Okay, so let me tie in some things real quick before I give you your next problem. Why did this one have no solution on the graph? What told us no solution? Or on the graph, on the previous problem? What was not there? The red vertical line was not there. This one, though we had multiple red lines, only one of them was within the domain. Your angles have to add up to be 180. That was not possible, so it had to be angle B there. So one solution. Here's one for you to try, and then we'll look at one that has more than one solution. Okay, so try this one first. Now let's take a look at example 4 of what happens when you have more than one possible answer. So I will show you their pictures in a second, but let's first look at what the calculator looks like. They've given us completed set A. So on my calculator, I'm gonna come over here and I have completed set A. Angle is 45, angle or A is 18. By the way, to have more than one solution, your angle has to be less than 90. That's just a fact. Now on this one, I don't have the angle, second angle, but what I do have is a second side length. C is 24. So I'll say that again. If you're gonna have more than one solution, it's a requirement that A is less than 90. Okay, I look and I see multiple solutions here, a whole bunch if you zoom way out. I'm gonna look, the most you can ever have is 2. So all I'm gonna look at are the first 2 positive occurring. Negatives aren't real. So I'm gonna look at these 2. These are the first 2 I'm gonna look at. So remember how I said this earlier? How if you have a triangle, and I'm gonna do my best to give you a 45-degree angle here. If this is 45, we're gonna ask ourselves, is it possible that I have an angle that is 70.5? Is it possible to have one that's 109.5? So let's just try to draw them out. Knowing, let's see, if that's A, I don't know where C's got to be necessarily located. I'm just going to put it here. We'll put that as 24, which means C is there. Is it possible that that could represent, oh, that's 18, that could represent right there 70.5 degree angle? Is that reasonable? Yes. The first answer is always reasonable. This question is, could we have one where the A comes through this way, instead of it 18 going this way, could the 18 be swung this way, and the angle be greater than 90? And the answer is yes. There's a possibility that that could be 109.5 there. So I'm trying to show you how you have more than one solution with 18 there, or it could be 70.5 on this one. So there are 2 possible solutions. So there's their little drawing. I think their drawing is a little confusing. So what I'm going to do is they do separate it out, and I'm going to take this one here, and we're going to solve this one. If it's like, I'll do that first, and then I'll get the other picture in a second. Okay, so let's solve it as if the triangle looked like this, where it's this way. So we just found angle C is 70.5 degrees. Okay, y'all tell me, I've been talking a lot. How would I find angle B here? Very good. So for this one, we would say 180. Whoops, that's an ugly 180. Let's try that again. Look like a 1 infinity. 180 minus 45 minus 70.5. Now I know it says round to the nearest degree. I'm going to round to the nearest tenth to make more sense out of what we do today. So I'm going to take 180, subtract the 45, and then subtract the 70.5. And I get 64.5. So that's 64.5 degrees. Now, to get my last set, I'm just going to use law of sines again. Remember, we had this as our completed set the whole time. And so now I'm just going to solve using for 64.5. So I come back over, I still have my completed set in 45 and 18, but now I'm going to use angle B as 64.5, and my unknown is the B here, which calculator tells us when I round is going to be 23. 22.976 is going to round to become 23.0. 23.0. So that's the solution set for that triangle if it were this way. Now there's also a possibility, I'll come around like this slide, hang on, don't panic. There's also another possible solution here. The triangle could also look this way. So instead of the 18 being swung this way, the 18 could be swung this way. And in this particular case, we found that this angle was 109.5. And we got that from the calculator earlier. So now I'll ask the question, how would I find out what angle B is? Every triangle, Adriel, has how many degrees? Every triangle has how many total degrees?
180.
180, there it is. So I take my 180, I subtract my 45, and I subtract this 109.5. Whoops, let me try that one more time. I'm struggling with the 100s here. 109.5. So I type that in my calculator. Let's see what we end up with. 109.5. I get 25.5 degrees. $25.5. So that would go there. Now to finish off this problem, again, we still have this completed set that we've had the whole time. I would then change my angle B to be 25.5. So I'll come over here, I type in 25.5, 25.5, and we get our final solution. When I round that, that's going to round to 11.0. So we came out with some pretty clean numbers there for the side lengths. And that's how you would solve it if it has more than one solution. So in a summary here, between example 3 and example 4, you have no solution if you do not see any vertical lines. You have one solution if when you look at it, you only see one line, or if you see multiple lines, but the other angles, the other intersections add up to be more than 180 degrees. You have so this one was only 1 because that was over 180. This one was 2 because both these two angles added, whether you did 45 plus 109 or 45 plus 70.5, you still are less than 180. All right, so I've talked a lot here. Let's try this one. So I have a completed set that's 24 degrees. I have an A length of 13 and a B length, I don't know the angle, a B length of 15. Here's my question for you. I see that there's multiple intersections here. I'm only concerned with those two, the first two that occur. That's all you're ever concerned with. If those two angles were combined to our first angle here of 24, would we still be under 180 or do we go over? Specifically, 152 plus 24. Is 24 plus 152 more than or less than 180? (24 plus 152 is less than 24 degrees plus 152 degrees equals 176 degrees. That's for angle B. I'll call it B2. The first B is always good if it shows 1. It's just 28 degrees when you round. So that means this answer choice is going to be correct. To get angle C's, you would subtract. So this is how they got there. So C1 would be the 24 minus 28, which would equal 128. And since we're rounding, the second C down here would be the 24. What did I do? I'm sorry. That's supposed to be subtracted from 180. Let me try that again. 180 minus the 24 minus the 28. That would give us 128 degrees. This one would be, sorry, let's try this one more time. 180 minus that 24 minus 176, which is approximately 4 degrees. So that's how you would get those numbers for that. I'm not going to do the law of sines there, but that's how you could figure that out. Okay. So in summary, you can use this graph to see if one or more exist. If you want to do algebra, what you would end up with is a non-real calculation. That's how it looks. So we spent a lot of time on law of sines. I've only left myself about 23 minutes to go over law of cosines, so I'm going to pick this up. So when do you use law of cosines? Well, the law of cosines, this formula here, are used anytime you do not have a completed set. So now that I've explained more of this, this is for when you do not have a completed set. Have a completed set. That's when we use the law of sines. Ugly have right there. Okay. So 3 formulas. They're very similar to the Pythagorean theorem, but they deal with triangles that are not right triangles, where the Pythagorean theorem only worked. Here is the Pythagorean theorem. That portion right there only works with the right triangle. This works with every triangle. So the algebra on this really takes a long time, but the calculator can go super fast. At this stage, I'm actually going to go to my calculator here. I'm going to open up law of cosines. Here's the problem. A triangular area of lawn has sprinkler located at each vertex. If the sides of the lawn are 19, 24.3, and 21.8, what angle of sweep should each sprinkler be set to cover? So here we go. We have some type of yard, and they don't tell us anything. So I'm just going to draw a random little triangle there. Really what they point out is that the shortest side is 19 feet. The longest side here, this would be the longest side, is 24.3 feet. And the middle side is 21.8 feet. And it says, what angle of sweep should each sprinkler cover? So we're looking for the angles. Do I have a completed set on this problem? Do we have an angle and its side length? No, we don't. So I can't use the law of sines. I got to use the law of cosines. So the law of cosines works like this. A squared equals b squared plus c squared minus 2bc cos a. Now for my calculator, basically what's always going to do is it's going to solve for a completed set. So whatever you plug in the place of A, whether it be angle A or side length A, my calculator will solve for its partner. That's how my calculator works. I'll say it one more time. No matter if you're given side length A or angle A, whatever you plug in one or the other, this calculator will solve for the opposite. It'll solve to find that partner, that pair. So in this problem, A is 19, B is 24.3, C is 21.8. Our angle is unknown. What happens is it does all this algebra for us, and we find out that angle A is 48.3 degrees. 48.3 degrees. That is angle A, 43.8 degrees. That kind of looks like 100. Let me. 48.3 degrees. Okay, so that's that angle there. And so how would you find the others if my calculator only gave you one and nothing else? Well, then what you would do is just switch the order. So again, whatever you put in the place of A, this will solve for its partner. So if I wanted to find B, I would just rearrange it. Like I'm going to put the 24.3 where A was. So this time I'm going to switch it. I'll just switch 24.3 and 19. So look what I'm done. On my calculator, all I did is I switched the location of 24.3 and 19. So this will now give me the angle that's across from 24.3, which will happen to be 72.7. 72.7 is across from the 24.3, 72.7. And if I did it one more time, and I wanted to find angle C, I need to put the 21.8 in place of A. So 21.8 is going to go here, which means 24.3 needs to go there. So whatever's in the place of A on my Desmos calculator, it's going to solve for the partner on the graph, which is, that rounds to be 59. It rounds to be 59.0. That's ugly, 59. Let me try that one more time. 59.0 degrees. And so if you add those up, you could check your answer, but those should add up to be 180 degrees. 48.3 plus 72.7 plus 59, 180. See how that worked? Now, if you want to know the algebra, how would the algebra work? Well, I'm only going to do it one time. I'll just do the A portion. We know A was 19, so you'd have a 19 squared equals B squared, which is 24.3 squared, plus C, which was 21.8 squared, minus 2 times B, which is 24.3, times C, which is 21.8, times the cosine of capital A. You can see this work's going to be a whole lot. I'm going to do one calculation in the calculator, so to make it easier, I got to move everything around to get, I'm solving for A here, so I need to subtract 24.3 squared and subtract 21.8 squared. So right now what I have is 19 squared minus 24.3 squared minus 21.8 squared equals -2 times 24.3 times 21.8. You getting tired of watching me do this yet? Cosine capital A. Now to get cosine by itself, here I'm going to divide all of this. Divide the parts that are multiplying. So the 24.3, the -2 times 24.3 times 21.8, and divide that by both sides. And that eliminates all of that. And the last thing I would do is I would take an inverse cosine. So cosine inverse of all of that fraction right there will give you my answer for just angle A. So all this work would only find me angle A. But that's the algebra that's required if you want to do that by hand. Does that look fun? No. I don't think it does. Let's check it out to see if Mr. Voorhees knows what he's doing or if he made a mistake here. Cosine inverse. We're going to have a big fraction, so I'll go ahead and hit fraction out. 19 squared minus 24.3 squared minus 21.8 squared all over -2 times 24.3 times 21.8. I got 48.3. Look what answer we had for angle A. 48.3. Now, which one was quicker? We could have solved this problem 3 times by the time I found just one angle. So law of cosines by hand is really slow, but by calculator, it's pretty fast. All right, I have one for you to try. I would highly suggest you try my calculator. DOL, this would be number 4 for you. All right, so now let's take another look at a triangle. So this time, let's just say the instructions weren't there. So you don't have these instructions, let's just pretend. So those are gone. And you just see that triangle. So this is more like a test question. I'm not going to tell you what to do. You'd have to solve for. What you need to look for is, do I have a completed set? Right now, do we have a completed set? No. If you don't have the completed set, we do the law of cosines. So what I'm going to do here is that same law of cosines, but I'm not actually going to solve it all out. I would just say that a squared would equal your b squared, which is 12 squared, plus your c squared of 14 squared, minus 2 times b times c times the cosine of 39.4 degrees. Now that would be the algebra you'd have to do. Well, if you don't want to do that, just come over here. We don't know A, so I'll put an X there. I don't know little a. Should replace, should revise. I do know little b is 12. Little c is 14, or side length c, I guess I should say. Angle A is 39.4. Now I get my value for lower little a. This is going to round to be 9.0 even. Now this problem has two different errors, and to address them, one of them is, you see how it says round to the nearest degree? Well, they didn't even round this angle, so it makes it problematic because we would have an extra 0.4 at the end. So what I'm going to do to try to get away from this problem has a lot of rounding errors if we don't round it differently. I'm going to round this to, let's just change it to 8.964. 8.964. I know I've been rounding to different. I'm going to change this one just because this angle is different, and it'll help us come up with a solution that's real. So now I have all three sides. So if you wanted to, I have a completed set. You could switch over to the law of sines, but with a calculator, I think it's almost quicker just to keep on doing what you're doing, but just rotate around. So now let's say we want to find angle B. If you want to find angle B, treat it as if this were A and this were B now. So just kind of switch it for the calculator's purposes. So for the calculator's purposes, I'm going to say little a is now 12. Little b is going to be that 8.964 that we just got. So I didn't want to round this is called the intermediate solution there. I wanted to wait just to make sure these other ones are better going off of it. And c is 14 still. We don't know our new angle A. So I'll type that in. I see I get 58.2. I'm going to go to the nearest 10. 58.2 for angles. 58.2. That's my angle there. And so now we could just subtract from 180, but I want to make sure I did this correctly. So I'm going to type it in the calculator and see. I'm going to pretend now like angle C is A. So I'm going to swap it with B here. I'll just leave this one as C. I'm going to swap these two now. So now little a is going to become 14, and I'm going to make little c become the 12. So I just swapped them, and we don't know the angles. Now let's go over here and click. I get 82.4. 82.4. And if I want to check, I can take my 180 and subtract 39.4, subtract the 82.4, and subtract 58.2, and I should get 0. Actually, I don't even know why I put the 180. I should have just said 39.4 plus 58.2 plus 82.4. 180 on the dot. So we did do it correctly. All right, so there is using law of cosines, even if you don't have all three side lengths, if you do have an angle to begin with. All right, so I have this one for you to try. So now let's move on to area. So area, there are two formulas that solve for area of a triangle. I have these linked, so let's go back over to Desmond's calculator. And I have it linked as Heron's formula, but truthfully, only one of these is technically Heron's formula. But then over here, I just linked it as area of a triangle. So Heron's formula is one way of getting an area without having to find what we call the apothem, if you remember that from geometry. It's this formula where you take half of the perimeter, that's a plus b plus c is the perimeter. If you take half of the perimeter and you take the square root of half the perimeter times half the perimeter minus a times half the perimeter minus b times half the perimeter minus c, you'll get the solution. Well, that's a lot to type in, so I just created a calculator for us. And we'll solve this really simply. Okay, so for this one, it says find the area to the nearest tenth. And they gave us side lengths. Well, if you've opened up the calculator, this will do the formula for you. So angle or side length A is 47. 47. Side length B is 53. Side length C is 44. I don't know any angles. If I did, it would give me the answer on this next formula you're about to see. But if you have the perimeter, you can solve for the area of the triangle using Heron's formula. It's going to be, the area will be 978.6 feet squared. And that's using Heron's formula, S times S minus A times S minus B times S minus C, where S equals half of A plus C, whoops, A plus B plus C. There you go. And that's Heron's formula. Really simple using that calculator. And so here's one for you to try, but before you actually try it, I'm going to just, while I'm on this calculator, show you the next problem. There's also these formulas as well. Okay, so what happens if you don't have all three sides? Well, you can solve for your area this way. Notice how I have it plugged in here of half AB, C. So this time I don't know, I'm going to say I know two side lengths. So I'll put those in as A and B here. So let's just say you don't know this side length. We'll take that off. We know the first side length is 39. The order doesn't matter here. Second side length is 52. And I know my angle is 25. That's the capital, 25.89 degrees. When I type that in, this equation now shows me my area is 442.8 when I round that. Area equals 442.8 inches squared. So now I have two DOLs. You can try off of this. And we use the formula here. Area equals 1/2. This one, it was technically B times C times sine A. It's technically what I did there. But I just used my calculator. I've typed in my two side lengths and my angle. So the calculator makes those really simple. So now you can try these two problems. This DOL for example 7 and the DOL for example 8. All right, to finish up this lesson, there's two DOLs. One of them's on your lesson exam. I'm going to do that one first, just so we don't run out of time. It says here, Owen's house is 12 blocks away from the library, 8 blocks away from the school. The library is 9 blocks away from the school. What is the approximate measure to the nearest degree of the angle between the path of Owen's house to the library and the path of Owen's house to school? Well, first thing I want to address, this does not have a right angle. So I can't use sine y, cos x, tangent is y over x. So we have to solve it either, it does not tell us that there's a right angle, I should say. So we have to be sure of our answer, we have to use either the law of sines or cosines. Which one would I use in this case? Law of sines or law of cosines? Why cosines, Airly? There's no pairs. So we're going to use law of cosines. Since this is the angle I'm looking for, I'm going to call that A. So I'm going to go to my law of cosines calculator, and we're going to say little a is 9. I'll just call this one B. This one C. We'll say the library, across from the library is the path for B, which is 8. And then that leaves C to be 12. I already had those typed in. That's great. My answer here would be 48.6 degrees. What am I supposed to round to? It says the nearest degree. So it'd be 49 degrees. It looks like to me when I round to the nearest degree, I get 49 as my solution, 49 degrees. Okay, now let's take a look at this ACP problem. It says observers 2.32 miles apart see a hot air balloon directly between them, but at the angles of elevation shown in the figure, 28 degrees and 37 degrees. Find the altitude of the balloon to the nearest foot. So we're trying to find the height of this balloon here. Let me see if I can separate it. No, I can't. All right, there you go. I just went trying to blow it up a little bit. Okay, so this is what we're working with. We want to find the height of this balloon. That's what it says. Find the altitude of the balloon, which means height. So I'll put this here, and I'm just going to leave it as a y for right now because it represents a vertical height. Well, to do so, some students just think, well, I can tell that this is a 90-degree angle, and I can use my psi y stuff, and just knowing that here I got a right angle on both sides, and so I just need to cut this in half so I have this part of the triangle. Well, this is not directly in the center, and the way I know that is because these angles aren't the same. So before we actually go about solving this triangle that way, which we will in a moment, what I'm first going to do is see that since I have two angles in the sine length here, I could actually get a law of sines by subtracting from 180. So I'm going to go over to my calculator, specifically the law of sines, because that's what I'm going to use. And I'm first going to find out how many degrees are for that angle. Let's see, 180 minus 28 minus 37. I'm getting 115 degrees. So let me write that in there. This is 115. And the reason it is, it's 180 minus that 28 minus the 37. Now, what I'm going to do next is, now that I have a completed set, I'm going to solve for a side length. So let's just solve for the one across from the 28. So I'll come to my completed set here. I have an angle of 115 degrees, and its side length is 2.32 miles. Where it says to the nearest foot. We'll have to take that into account in a second. And the angle B is 28, but we do not know our x. And so let me zoom in on this here, and our solution is 1.202. Let me get a different color. 1.202 miles. Okay, so now that I know that, what I can do is come back, and now we can solve this triangle. So now I'll solve that triangle here. Let me go ahead and show you which triangle I'm now going to solve. Is now this one, because I have enough information to do so. I have this piece, and this piece. Let's see. So I copied that over. And so to fill in our spots, we're looking for this y value here. We know this is 1.202. And we have an angle. So I have a completed set, and I'm looking for this y value. So now I want to come up here and say my completed set is the 90. And by the way, you could use psi y because I have a y in the hypotenuse, but I'll just stick with the law of sines for now. My angle is 90 degrees. My side length is 1.202. My other angle for B is 37 degrees, and this intersection will give us our y, our height. It says it's 0.0723. So here I just come up with 0.723. Now that's in miles. I forgot to write that miles there. We want the answer to the nearest foot. So 0.723 in miles. If you want to convert, for every 1 mile, there is 5,280 feet. I heard a student once say it's 5 tomatoes, 5 to 8 O's, 5 to 8 O's, 5 tomatoes. That's what it sounds like. And so if you multiply across, we should get our solution here. So to the nearest foot, 0.723 times 5280. I'm getting 1,865 feet. 1,865 feet. 1,865 feet. That would be our solution there.